And the final speaker for the first session is Laura Nichols from Vanderbilt University. She's a computational solid-state physicist and works with Socrates Pantelidis. She's going to tell us about defect activation through hydrogen release in semiconductors. Please welcome Laura Nichols.
Thank you, guys. So like you said, I'm going to be talking about defect activation through hydrogen release in semiconductors. I am at Vanderbilt, and we have collaborators at the University of Florida, and of course couldn't do this without the resources from my fellowship. So to dive right in, I'll give a brief background because I know everybody doesn't have a background in semiconductors. So of course we know semiconductors can be used in many applications, from LEDs and solar panels to the computers that we use every day. These computers are based on transistors, so primarily a silicon-based MOSFET that is basically a semiconductor allows us to turn the current on and turn it off, ones and zeros, you have computing. Silicon is relatively abundant, and it can be made very cleanly, very easily, so it dominates in practical applications. But there are other interesting materials like gallium nitride that have properties that allow them to work at higher temperatures, higher powers, but they have more defects, and not as much is optimized and known about them as silicon. So what we want to do is use a first principles physics-based approach to figure out what defects are likely to be present in gallium nitride and which ones contribute the most to device degradation. Because if they're there, but the device still works great, we don't really care about it. So there can be defects in both kinds of devices, mainly in silicon-based MOSFETs. You get these interface traps where the silicon dioxide and silicon don't quite match up, so you have dangling bonds there. And then in gallium nitride, you can have different defects like gallium vacancies, nitrogen vacancies, things like that. And here I show that hydrogen has come in the fabrication process and passivated these defects. So it makes them to where they don't interact with the carriers as much, they're not going to trap them, and we call those deactivated defects. What we care about is when the system gets excited, it starts vibrating, and that hydrogen gets kicked out, then the defects become active. Carriers coming by the defect will likely get trapped there, the device degrades, and we want to figure out what makes those hydrogens get released, what process leads to that. So first, how does the system get excited? How does it vibrate more and more? Well, there's a well-known case of radiative capture. So here I show this is what the energy bands look like in a material, specifically a semiconductor. You have the valence band where mostly all of the states are occupied with electrons. Then you have the conduction band where it's mostly empty with some electrons moving along. And then you have this gap in between. And you can have localized defect states in the gap that can capture those carriers. That would be one of those dehydrogenated or activated defects. So as the carrier comes along in radiative capture, it drops down into the defect and shoots off a photon. So the energy mostly leaves the system. What we are interested in considering is the scattering case, which is it doesn't necessarily get captured and lose all of its energy. It loses some energy, drops it into the defect, and then continues on. And that energy, instead of being released as a photon, gets transferred into phonons, which are collective atomic vibrations within the material. And the nature of hydrogen being so much smaller than the other atoms in the system means that it's going to move a lot more, and it will eventually get kicked out. There have been some engineering level models on this problem that have made a lot of progress. One such model assumed that the carrier had to have an energy above a certain activation energy, and it was a one-shot process. One carrier would drop all of the energy needed to get it over the barrier and activate the defect. Other models have improved on that by considering multiple excitations. So this is the energy levels in the vibration spectrum. And as energy gets dropped in, sometimes it goes up the ladder, sometimes it goes down, but eventually you see it come out. But both of these models require a lot of data fitting, and we want to get away from that because we want to be more predictive. So how can we look at this problem from a first principles approach? Well, no one has considered the so-called inelastic scattering, where the carrier just loses some energy from a first principles approach, but there's extensive literature on the capture problem from a Fermi's golden rule transition rate. It's a standard quantum mechanics equation. And we started there because it's a relatively simpler case and we have things to compare to. So in the past, there was a paper published that calculated what we call equilibrium capture. So instead of coming far from the defect, it's hanging around the defect, gets perturbed by the phonon vibrations, drops down into the defect, and dissipates the energy. But in order to calculate that, it's a really hard problem to do. So instead of considering all of the phonon vibrations, they had to average out all of the vibrational modes before and after capture. And that meant that their model was very, very sensitive to the energy being dissipated into phonons. So you can see this y-axis is a logarithmic scale, and even slight changes in that energy produce orders of magnitude differences sometimes. There was also a paper done by the group that I'm in prior to my arrival, where they considered non-equilibrium capture, but it was from the perturbation of the defect itself. So if it's not around the defect, it approaches the defect, it can act as a perturbation itself and cause the capture. They did consider all of the phonon modes in the system, but they were only able to do Monte Carlo sampling of how many modes could participate at the same time, because it's a huge problem. And just to give you some scale of the problem, as an example, for our proof of concept, we're working with a 512 atom silicon supercell, which is not very large, but it's basically close to the minimum of what you would want for a defect calculation. For every single mode in the system, which we have 3n minus 3, the number of atoms in the system, 3n minus 3, we have to slightly displace along the phonon vibration eigenvector, recalculate the wave functions to get a wave function derivative, and then we have to run our code to get the transition rate. Now, we use VASP, which is a large commercial software to do the density functional theory calculations to get the wave functions. It is very well scalable with nodes, so you can always throw more computing power at it and it will go faster. But the code that we had was not integrated well with VASP, and it was not fully parallelized, so it took a long time, hour and 15 minutes per mode, and we have many modes in our system. And even if you threw more computational power at it, sometimes it would go slower because it just didn't even help. So if you multiply out all of that time, the time for one calculation times the number of modes in our system, and thankfully each of the phonon mode calculations are independent, so they can run in jobs at the same time. On average, if you let 4 run at the same time, that takes 24 days just in runtime and 2,700 node hours. So if you look on Iris, the NERSC portal, the default allocation right now is 500 node hours per year for fellows, which you can get more, you know that. But this is huge. It's huge, and it's not feasible. So against my advisor's wishes for a little bit, because he's physics and not computational, I begged him to let me invest in the code. So I optimized all of our code, fully parallelized it, and the huge thing was implementing parallel I/O, because the wave function files are humongous, and was able to take it to an hour and 15 minutes down to 8 minutes. And it's now fully linear scaling with the nodes. So as the system gets bigger, as the problem gets more difficult, it is completely scalable now. And now the time to do this calculation with the same assumptions is 5 days. And little bit less than 1,000 node hours, which is still very, very large, but reasonable. It's something that we can do. So we have done those calculations. We have a paper under review right now. We did the non-equilibrium capture problem that we are interested in. And then we also benchmarked it against equilibrium capture with the caveat that in this case, because of a fortuitous algebra trick that we found, we were able to include all of the phonon modes instead of using the approximations used before. So not only is our model now fully scalable, it's actually more accurate than previous models, with the caveat that the experimental data has large error bars on it, really, and all of these calculations have large error bars because this is a very hard problem to solve, so there's not a lot of work that's been done, and there are a lot of improvements that can be made. So that's not what my work is on. It's on hydrogen release. So now how do I get to hydrogen release? Okay, I've solved the capture problem, but one of the key things about the capture problem is that you have a displacement between the initial equilibrium positions and the final equilibrium positions, which of course you would, because when the carrier drops into this localized state, it gets very, very localized, and the atoms are going to want to move around to accommodate that. But it's been widely thought that in inelastic scattering, you're going from a delocalized state to another delocalized state. You're not going to have that. So you're not going to get the multiphonon emission that we need for these processes to happen. But I, in my investigation, have been able to show that even going from one band state to another, these states are both very highly delocalized, but they are distributed differently, and they produce a large enough displacement to get that energy dissipation. So now we know how to get the energy from the system, and that would be even more magnified if we were able to find resonance states. So this image is actually from a collaborator looking at a different defect, but this is a band state that is super, super highly localized around the defect. So those would really dominate this process as well, and we're searching for that. And once we find those states that produce a large enough displacement, we can take the energy difference, and one caveat to note is there are a lot of possible transitions. So this problem just keeps growing and growing and growing. We split the energy across all of the phonon modes to see which modes get excited more. We average over our final states using the theory based on Fermi's golden rule that we developed for capture. Then we take, based on actual device specifications, a carrier density as a function of energy to average over the initial states to get an average rate of energy transfer into each of the modes. That then needs to be translated into the hydrogen motion. To do that, we take a page from the rogue waves research. So this is not my primary area of research, but rogue waves theory is based on you have these different waves moving in different directions on the ocean of the surface, and every now and then, seemingly randomly, you will get a huge wave because just fortuitously they add up together. This is a rare event, but we think that it could be significant in the hydrogen release process. Monte Carlo sampling does not adequately represent the tails that would give you those huge kicks. So we took a developed rogue wave theory, which is to add a bunch of sine waves together, basically, and we adapted it to work with arbitrary amplitudes and frequencies and for three-dimensional phonons. So I'm basically getting like 3 PhDs. And that gives us our probability distribution. And then we set a bond length threshold. The fraction above the threshold and below gives us the proportion of activated defects in the device. All we need from our engineering collaborators is the number of precursor defects in the device that they can estimate from other measurements. And then we can take that and integrate it out to see as a function of time how many hydrogens are getting released. and map that directly onto experimental results like the threshold voltage shift in the devices to now be predictive. Instead of fitting this data, that's what was done before, this data was fit, we can now be predictive. So that is it. Do you guys have any questions?